Predicted topics for paper 2, AQA A-level chemistry exam 2024. This is part 2 for organic chemistry topics. We had part 1 for physical chemistry topics. The first topic, which will definitely be in your exam, is the analytical techniques. So they can either provide you with an IR, NMR, and ask you to find the structure, or they can just ask you to give justification of the different peaks. So let's have a look at the IR. The most important peaks in an IR is this peak for the carbonyl group. This is around 1720 centimeter minus 1. This is going to be strong and sharp peak. This is for carbonyl. It could be for ester, for acid, aldehydes, or ketone. And the second most prominent peak here is the broad peak for the OH. It's around 3,400 centimeter minus 1. This is for an OH. Remember that if they give you the IR for one compound and ask you to figure out after a reaction what would be the changes in the IR, look at the functional group, how's it changed, and use your data book to find the new peaks and how and which peaks is going to disappear. And remember that one of the changes that you have to refer to is the fingerprint region. So the fingerprint region will always be different if you do any small change in the structure. So for a reactant that changes into a different product, then the fingerprint region will always change. Carbon 13 NMR, you can use this to differentiate between aldehydes and ketones and the esters and acid, because the carbonyl carbon will appear at a higher value between 200 to 120 if it's aldehydes or ketone, but it's going to be a bit to the right, so between 160 and 185 if it's ester or an acid. So if you find any peaks within that region, that means that you have a carbonyl group. Also, carbon 13 can be used to determine how many, the number of chemically non-equivalent carbons. So in this case, we have 4 different or chemically non-equivalent carbons in our compound. Um, Carbon, which is next to an oxygen or chlorine, are easy to spot because they come in this a bit to the left region, something above 60 and maybe 90. So something like that, it's either a carbon next to an oxygen or a carbon with a chlorine. Carbon-carbon bonds, or carbon which is next to a carbon, this is going to be the ones at the far right. This is usually 20 or less part per million, and then the carbon next to carbonyl is above 20, but it's not too far away. And then we have the proton NMR. Proton NMR can determine the number of chemically non-equivalent proton. That depends on the total number of peaks. So if you look at the table here, we have 4 different peaks. So there are 4 different chemically non-equivalent protons. The integration will give you the number of hydrogens that give that particular signal. So here it's 3311, for example. That means we have 3 protons, 1 proton, and 1 proton. Each signal will give you, the integration will give you the number of protons. Sometimes they give you the integration as ratio rather than particular number that gives you the number of the protons. For example, like 0.6, 0.6, and 0.9. This is going to be 2, 2, and 3 protons. The chemical shift will, you can use the data from the data sheet to determine the most probable chemical environment, and then splitting it will tell you about how many protons are there on the adjacent carbons. Remember that OH doesn't split the protons on the carbon, and also the protons on the carbon do not split the OH, so OH will always be a singlet. Even if you cannot figure out the correct structure at the end, remember that your interpretation will get you most of the mark. So the chemical shift, if you have a hydrogen on a carbon next to a carbon, this is going to be to the far right. So it's going to be low value, less than 2 parts per million. If you have the hydrogen on a carbon which is adjacent to a carbonyl. This is around 2.5 part per million. A carbon next to an oxygen, this is a bit to the left, so something in between 3.5, 4.5 part per million. And carbon chlorine as well is a bit shifted towards 3 point something until 4 till 4 point something. Of course, they're going to give you either the molecular formula or the empirical formula where you can determine whether you have a carbon next to an oxygen or carbon next to chlorine. The splitting pattern is very important to determine the number of hydrogen on adjacent carbon. So if it's singlet, that means there is no adjacent hydrogen, or it could be next to an OH, or it could be an OH itself, like this one. For example, this compound here, we have this one 3.7 singlet, one proton. This was for an OH. A doublet means there is only one adjacent hydrogen next to it, like this one, these three protons, 1.2, it's a doublet. That means it's CH3, which is next to a CH2. This is how you should interpret your data. If it's a triplet, then that means we have two adjacent hydrogens. And if it's a quartet, then that means that there are three adjacent protons. Like this one, this is a quartet, so it's 3.9 and it's only one proton, which means it's a CH and it's next to a CH3. So this is the hydrogen here. Reaction mechanisms. So rule of thumb, remember that curly arrows go from electrons to an electron deficient atom or towards a single bond to make a double bond. This is how your curly atom direction will go. Don't ever get mistaken and think that curly arrows shows the movement of atoms. It shows the movement of electrons. There will be several reaction mechanisms definitely in your exam. There will be questions with missing arrows where they ask you to add the extra arrows and the lone pair of electrons. There will be a question on organic essences as well, and there will be a whole mechanism question as well. So remember that when a bond is added, another has to be broken unless you make a positively charged oxygen or nitrogen with a dative covalent bond. So if you have something like this one with this is a hydrogen and methyl, this is a nucleophile, and it attacks, for example, something like this carbon electron deficient carbon, then this is gonna go here and this bond has to break. And then when the oxygen is added, the oxygen is going to have a positive charge, but eventually this proton has to leave because your product has to be a neutral. Let's have a quick look at the different reactions and mechanisms just to revise the main rules. So first of all, the radical chain reaction. So this is for alkanes, which are fairly inert toward most reagents. You need to use UV light and you need to use chlorine for the chlorination of alkanes. There are three steps: initiation, propagation, and termination. Initiation when the free radicals produced, propagation when more free radicals are produced, and then termination is basically when the free radicals react together to give you the products. CFC and the ozone layer is very common in your exam. It's also a free radical reaction. The UV light is used to create the free radical, and then you have the propagation steps where more of the free radicals are formed, and then you have the final step or termination step. Remember that chlorine free radical here is just a catalyst because it's regenerated at the end of the reaction. Nucleophilic substitution reactions, they all have the same mechanism. You just need to think about how the electrons are going to move and the curly arrow. Whether you have, this is for alkyl halides or halogen alkanes, when they react with a nucleophile. So nucleophilic substitution reactions are the reaction of alkyl halides with nucleophiles. The nucleophile could be an OH minus, could be a cyanide, or could be an ammonia. So always remember that the curly arrow, the movement of the electrons from the nucleophile toward the electron deficient atom, which is the carbon, because this is partially positive and this is partially negative. And as a new bond is formed, and the other one is broken. The same principle for cyanide here, and for the ammonia it's also the same, but remember, because ammonia is a neutral compound, we're going to have the ammonium one first, and then another molecule of ammonia will act as a base to take this proton from the ammonia. Remember the movement of the electron, and remember that when one bond is formed, another has to be broken, and if something leaves, the electrons have to go back to the molecule. Remember that for the hydroxide, this can be used to act as a nucleophile or can act as a base, depending on the reaction condition. So if it reacts as a nucleophile for substitution, you need to heat with aqueous sodium hydroxide. But if you heat with ethanolic sodium or potassium hydroxide, then the hydroxide ion will act as a base here, and they're gonna undergo, the halogen alkane will undergo the elimination reaction. So elimination reaction, then you have a base, something like hydroxide here. When we heat it in ethanolic potassium hydroxide, the double bond, the lone pair of electrons or the negative charge on the hydroxide or the base will take the hydrogen. Since the hydrogen is going to leave as a proton, the electrons will move towards making a double bond. We made a new bond here, so the bromide has to leave. That will give you the double bond here for the alkene. Remember that synthesis of alkene as well from alcohols will give you the alkene, but the mechanism is a bit different because we use a catalyst now, a hydrogen catalyst or acid catalyst. So there is a proton, and when there is a proton and you have an OH with lone pair of electrons, of course the curly arrow will go from this into the proton. That will give you an oxygen with a positive charge with three bonds. So this has to be broken now. The water will leave. That will give you a carbocation. So another proton has to leave from the adjacent hydrogen to make the double bond. So this is the curly arrow from the electrons between the hydrogen and the carbon towards the two carbons to make the double bond. In this reaction, this is a dehydration reaction, and we heat it with concentrated sulfuric or phosphoric acid, which acts as a catalyst. Electrophilic addition reactions are very, very common in your reaction, in your exam, especially in case of use of unsymmetric alkenes. So electrophilic addition reaction is the reaction when you add a small molecules to a double bond of carbon-carbon double bond. This is different from the nucleophilic addition to carbonyl, which is going to be a nucleophile attack. But here it's an electrophile because when you have something like hydrogen bromide, for example, so the curly arrow will go from the double bond towards the hydrogen, which is partially positive, and the bromide is partially negative. And remember that in case of unsymmetric alkenes, you're going to have two intermediates because the hydrogen can be added to carbon number one or to carbon number two. So that will create two different carbocations. One of them is a primary carbocation, which is less stable. The second one is the secondary carbocation, which is more stable. So because the secondary carbocation is more stable, it will be formed more in the reaction. And with the presence of bromide, this is going to attack the secondary carbocation. It also attacks the primary one. This is why you end up with two products, but the 2-bromopropane is going to be the major product because this is more stable, and the 1-bromopropane will be the less the minor product because this is less stable. Electrophilic addition reaction as well, it can be for neutral molecule like bromine. Remember the bromine water test for alkenes. In this case, you're gonna have, as the double bond approaches the bromine, one of them will be partially positive, the other one partially negative. We're gonna apply the exact same principle, the exact same mechanism. Addition of water or hydration, this is a specific mechanism because we use sulfuric acid as a catalyst here. So in case of sulfuric acid, the first step is the double bond going toward the proton here on sulfuric acid, and the bond is going to break, and then that will create the carbocation. Remember, if this is unsymmetric alkene, this is going to apply the same principle where we can have two intermediates, two carbocations, one is major, one is minor. And then once these two have been generated, the second step is that this sulfate ion will attack or will be added to the carbon with a positive charge. That would give you the ethyl hydrogen sulfate or whatever we have. If it's propyl, it's going to be propyl hydrogen sulfate. And then if you warm it with water, that will give you the alcohol. And then sulfuric acid will be generated back again in the reaction because sulfuric acid is just a catalyst here in this reaction. So the overall reaction here for senses of ethanol as well is that ethanol with water will give, in presence of sulfuric acid as a catalyst, will give you ethanol. Remember the nucleophilic addition reaction to carbonyl, we said it's going to be a nucleophilic addition, not electrophilic addition, because now we have a partially positive carbon and we have the partially negative oxygen. The cyanide, addition of sodium cyanide or potassium cyanide is an example of that. Again, when we add the cyanide will attack the carbon, and since it attacks the carbon, a new bond will be formed. So another one has to be broken, which is this double bond that will give you this intermediate. If you add an acid or water, then this is going to be added to the oxygen to give you the final product. The addition elimination reaction is the reactions of the acid chloride or anhydrides with nucleophiles like alcohols, water, or amines. So this reaction has two steps. The first one is the addition step. The second one will be the elimination step. So if you have your nucleophile here, it's again going to attack the carbonyl carbon and the acid chloride, and this bond is going to break. And then the second step is the elimination, where the chloride is going to leave, and then the double bond will be regenerated. Remember that the methanol here or the alcohol here has been added with a positive charge on the oxygen now, so the extra proton on the oxygen has to leave, and that will leave with the aid of the chloride that left in the previous step. And then remember, because the hydrogen is going to leave now, the electrons between the hydrogen and oxygen have to go somewhere. So they will move towards the oxygen. Now you get your final product, which is the ester plus hydrogen chloride. Esterification is the formation of ester from acid and alcohol. So any acid with any alcohol in presence of acid catalyst, that will give you the ester. Remember, the hydrolysis is the formation of alcohols from esters. So if you have ester and we use an acid and reflux in presence of water, that will give you the carboxylic acid and the alcohol. This is called acid catalyzed hydrolysis. We also have the base catalyzed hydrolysis, when instead of using water and an acid, you use an OH minus, and then this is going to give you the salt of the acid and then the alcohol. Remember that saponification is a specific type of the base catalyzed hydrolysis, and this is used to make soap. This is the triester of the glycerol, fatty acid glycerol triester, and this comes from natural fat or oil. This is very, very common in your exam, by the way. So if you heat with sodium hydroxide or potassium hydroxide, then that will give you the sodium salt or potassium salt, depending on which one you've used, which base you've used. Sodium salt or potassium salt of the fatty acid, which is the soap that we use, and then you're also going to have glycerol. Friedel-Crafts acylation, this is a type of the electrophilic substitution reactions of the aromatic compounds. Remember that for Friedel-Crafts acylation, this is very common in the exam, by the way. For Friedel-Crafts acylation, you need to generate your electrophile. First, this is acylation addition of or adding an acyl group. So we use aluminum chloride here to generate the electrophile. And then we have the electrophile. This is electrophilic addition, electrophilic substitution. So it's the electrons inside the ring. The benzene ring is going to attack the electrophile, and this will open the. Don't forget that will open the ring of the electrons inside the benzene ring with a positive charge. And then you have the deprotonation step, and don't forget the electrons between the carbon and hydrogen will go back inside the ring to regenerate the ring or the double bond. And then you're going to have the acyl group, which has been substituted for the hydrogen. And then nitration is another type for electrophilic substitution. For the aromatic system, you just need to know how to generate the electrophile here, which is the nitronium ion. This is by the use of sulfuric and nitric acid and heating at 55 degrees. The mechanism is exactly the same like the second step of the Friedel-Crafts. So the electrophile, the attack from the electrons, and then the hydrogen will move back inside the ring. The electrons between the carbon and the hydrogen will move back inside the ring to regenerate the ring, the electrons, the delocalized electrons or the aromatic system, and then you're going to have the NO2 or the nitro group substituted, being substituted for the hydrogen. And then finally, reductions. You just need to know what are the different reducing agents you use for your reaction. First of all, if you have cyanides, as then you can either use lithium aluminum hydride and then dilute acid that will give you primary amine, or you could use nickel catalyst with hydrogen at high temperature and pressure. This is used in industry because lithium aluminum hydride is quite expensive. That will also give you primary amine. If you have aromatic nitro compounds, you can also reduce this into amine, but the catalyst here is different, or the reagents are different now. So you should use tin with concentrated HCl and flux. The second step is the use of sodium hydroxide, because if you don't use the second step, which is the sodium hydroxide, then you will end up with the ammonium salt, so NH3Cl. So this is going to be the ammonium salt produced in the reaction. So use sodium hydroxide to give the amine or the final product, which is the neutral one. Finally, the organic synthesis scheme. There will be an organic synthesis scheme like this one in your reaction. You need to know how to answer these type of question and how to think about the different reaction. First of all, think of the role of your compound or of your reagent, whether it's an electrophile or a nucleophile, or if it's a base. And then look where the change in the product took place, and then think about how to make that change. And remember that reactions are either substitution, addition, or elimination, or let's say reduction, even though reduction is either a substitution or an addition, but we just going to say reduction for now. And then you need to think about whether the reaction took place on an aromatic ring or an aliphatic chain. So let's have a look at this one. So you have this structure here, step one. We substituted the hydrogen with a nitro group. So this is the electrophilic substitution reaction or the nitration. In your exam, if they ask you about the to name the reaction, it's electrophilic substitution reaction. Don't just say nitration. You can say nitration as well, but you need to say electrophilic substitution. Second step, we changed the nitro into an amine, and this is aromatic. So we remember the reduction for aromatic nitro groups into amine, which was the 10 with the concentrated hydrogen chloride. And then the third step, we added this acyl group to the amino group to make an amide. So this kind of reaction, what kind of reaction is this? Then this is going to be a nucleophile, and this is the acyl will come from the acid chloride or acid anhydride. In this case, for simplicity, we just can say from acid chloride. This is the addition elimination reactions. Step 4 here, the change here is the addition of this chlorine on the aliphatic side chain here on the CH3. This is aliphatic, so this has to be the radical chain reaction. So we use the chlorine with the UV light. And then the final step here is that we change the chlorine into an H2. You remember this is nucleophilic substitution when you make amines from alkyl halides. So this is we need to use ammonia in this reaction, and this is nucleophilic substitution reaction. Topic 4 is polymers. So remember the addition polymers for alkenes and condensation polymerization. So addition polymers, we can only see it in alkenes. And then the condensation polymerization we'll see condensation polymerization when a water molecule is removed, and usually this will be between a dicarboxylic acid with a diol, or a diacyl chloride with a diol, or diamine with dicarboxylic acid. Remember that naturally occurring polymers are proteins, and DNA proteins has been the subject in the exam for quite a few years. Maybe this year there will be a question about DNA. I would expect that there might be a question on the two types of polymers, the addition polymers and the polymerization polymers, and they might give you a 6-mark questions asking you to compare between them in terms of disposals, types of bonds, recycling, and all of that. Remember the addition polymers, when you have the double bond, whatever you have on the side, just remove the double bond, keep the substituents as they are, and then you just draw the remaining of the molecule within. And then when you have the condensation polymerization, it depends on what are we using. So if it's acid chloride or carboxylic acid with a diol, then it's going to be an ester. But if it's an acid chloride or acid carboxylic acid with an amine, then it's going to be an amide bond. Both of these hydrogen water molecules will be removed. Remember purification of organic molecules. You add water to remove the water soluble impurities during the washing steps. You add drying agent to remove any excess water like anhydrous magnesium sulfate or anhydrous sodium sulfate. You use a separating funnel to remove water soluble impurities from the products. And remember that volatile liquids can be purified by distillation, and if the boiling point is in the closed range, then we use fractional distillation rather than simple distillation. Remember that crystallization can be used to purify solids, and remember that melting points and boiling points can be used as a good indicator for purities, because impurities will increase the melting point and will decrease the boiling point. Tests for functional group. Last year exam, they had a whole question about tests of functional group, where they got all the tests, and they asked about mistakes in carrying out the test and how to uh, identify the structure based on the test. But it's worth that you revise these as well, because one or two might come up in the exam. I don't think there will be a whole question on the functional test for functional group. So potassium dichromate in acidic solution with warming, that will change the color from orange to green. This is the positive test. This is going to be positive for primary alcohols, secondary alcohols, and aldehydes only, and not for ketones or tertiary alcohols or even carboxylic acid. Tollens reagent, which is going to give you a silver mirror. This is positive for aldehydes, but not for ketones. Fillings and Benedict solution, when you warm them, there is a color change from blue to brick red. It's going to be positive for aldehydes, but not for ketones. So these three tests are to differentiate between aldehydes and ketones. And then bromine motor test. This is the change of color from orange to color. This is for the carbon-carbon double bond. And finally, sodium carbonate test for carboxylic acid, where adding sodium carbonate to carboxylic acid will give you carbon dioxide. So there is fizzing, and then the carbon dioxide gas you tested with lime water. Finally, the isomers, remember the and E isomers of alkenes. The D isomer is means that the two priority groups or the two big groups are on the same side, like here, and then the E is on when they are on opposite sides. Remember that optical isomers, when we have a chiral carbon, the carbon which has four different substituents, then the S and R optical isomer, they can be differentiated from each other by they rotate plane polarized light in opposite directions. And then structure isomers, remember that they will probably ask you in the exam to draw several isomers for a certain compound, or and they could give you some information about that particular isomer to and ask you to draw a